In this video, I want to walk through another example of finding a rate law from experimental data using the initial rates method. So here we have a reaction to determine the order between nitrogen oxide and oxygen. And so what we have is a reaction where we have NO plus O2 forming products. And we may not know the balanced equation for this at all. All we know is that we're combining NO and O2. We don't have a complete picture of what this reaction is. And that's okay because finding out rate dependence can help us kind of understand what that reaction looks like and what the products are and what it looks like when it's all balanced. So we ran 3 trials. In one, we varied the amount of NO, and in the other two, or in two of them, we varied the amount of oxygen. And we measured the rates for both. So I'm going to take these just two at a time, and I'm going to try to focus first on NO, and then I'm going to focus on oxygen. And my first goal is I'm going to try to get the order. Yeah, let's write this out. I'm going to try to learn ah, the order of with respect to NO. Then I'm going to find the order with respect to oxygen. And then I'm going to find the equilibrium constant. Or sorry, I keep saying equilibrium constant. I'm going to find the rate law constant. And lastly, I'll write my overall rate law. So let's start with that first one. So to figure this out, I'm going to essentially write out my rate law for my two experiments over one another and look at that ratio. And remember, our rate law is going to be equal to some equilibrium constant times the concentration of NO to some exponent times the concentration of oxygen to an exponent that we don't know. So um, I know that my rate, so let's write this out. So I've got my rate um, for experiment, let's do experiment 2 over the rate of experiment 1. That's going to be equal to, and I'll write out my rate law, the K times our NO to M times our O2 to the N, and I'll do the same down here. All right, so this is going to equal, now I'm going to fill in, pen's being weird. I'm going to fill in the information that I have experimentally. So I know my rate 2 is 6.0 times 10 to the negative 3 divided by 1.5 times 10 to the negative 3 for my rate for experiment 1. And then that's going to be equal to the constant I don't know yet. My concentration from NO is going to be 0.24 to that M exponent. And for that second one, my concentration for oxygen is 0.25 to an exponent that I don't know. So then we divide this all by the information for experiment 1. So I've got K that I don't know. I have 0.12 to the M for my NO concentration. And I still have 0.25 to the N for the concentration of my oxygen. So now I can come through and cancel out anything that's the same on the top and on the bottom. So that gets rid of K, it's the same. And it gets rid of the 0.25 to the power of N. They're the same as well. So now I can simplify this. I can divide that 6 times 10 to the negative 3 divided by the 0.5 times 10 to the negative 3. And when I do that, I get a value that's 4. So that 4 is equal to this 0.24 divided by 0.12 to the M power. And so when I divide that 0.24 by 0.12, I get, well, here we can do it like this even. 0.24 divided by 0.12, all to the power of M, which is going to be equal to 2 to the power of M. So now I just need to solve for M. So I'm going to take the log of both sides. So the log of 4 is equal to M log of 2. And now I can solve for M. M is going to be equal to the log of, can't spell log, the log of 4 divided by the log of 2. Which is going to be equal to 2. So that order with respect to NO, this is going to be equal to 2. So I now know that my M is a 2. Great, that's part of it. So now we can go on to step 2. I'm going to erase this piece right here. This is actually on the next page. The solution is for this example is typed out, so you can refer to it later. But I think it's helpful to walk through it like this way as well, instead of just looking at the information written after the fact, as it's kind of a lot. It can be a little confusing. Okay, did all that erasing. Now it's time to do a comparison between experiments 2 and 3 to find the order of oxygen. So I'm going to do this the same way I did it before, but now I'm going to be focusing on oxygen. So I'm going to look at the rate of experiment 3 over the rate of experiment 2. And I'm writing out my rate law. It's going to be K times my NO to the M. Well, actually, now I know what M is, right? It's 2. So NO to the 2 times O2 to the N, all divided by K to the NO squared, O2 to some exponent we don't know yet, N. And now I'm going to fill in the information that I know. And so I know that I have a rate of 1.2 times 10 to the negative 2 for rate 3, divided by 6.0 times 10 to the negative 3 for my rate for number 2. That's going to be equal to the K that I don't know yet, times a concentration of 0.24 for both of my NOs squared, times 0.5 to the N for my oxygen. And then for 2, experiment 2, it's 0.24 squared, and then 0.25 to the N. And so I can come through and cancel everything that's the same. And so these K values cancel out and these NO values cancel out because they're same on the top and the bottom. And so now I can simplify this. So my 1.2 times 10 to the negative 2 is going to be divided by my 6.0 times 10 to the negative 3 is going to give me a value of 2, which is going to be equal to that 0.5 divided by 0.25 to the N, which is really equal to 2, right? To the N power. So I can take the log of both sides. I could also recognize this as first order because 2 to the power of 1 will equal the same numeric value of 2. But let's go through it. So then what I can see is that the log of 2 is going to equal to N times the log of 2. And so N is equal to log 2 divided by log 2, which is equal to 1. So it's first order with respect to oxygen. So that means this N here is a 1. Great. All right, so now we have the orders of our reaction. Now we just need to find K. I'm going to do some erasing. Right, now we need to find K. So we're going to just choose any one of our 3 experiments and plug all the information that we have in now that we have the orders and just solve for K. So I'm going to use experiment 1, but you could use 2 or 3. So I'm going to start with experiment 1. And so for this, I know that rate is equal to my rate constant times the concentration of NO squared times the concentration of my oxygen to the power of 1. And so that's just incorporating that order information that we just found out. So my rate for the first one is 1.5 times 10 to the negative 3. That's equal to K times the concentration of NO is going to be 0.12. So 0.12 squared times 0.25 for my oxygen to the exponent of 1. And now what I need to just do is solve for K, trying to highlight it. So my K is going to be equal to this 1.5 times 10 to the negative 3, all divided by 0.12 squared, 0.25 to the power of 1. And so if I plug that into my calculator, I'll get that K value. And so that's going to be equal to 0.417. All right, so K is 0.417. Now I need to figure out what its units are, right? So for that, the overall order for this reaction, let's switch colors. The overall order is 2 plus 1, because I'm just adding up my exponents when I do this. So I have a third order overall reaction. So that means that my K units need to reflect that. And so if you look back up here, when we have an overall order of 3, we're going to have 1 over molarity squared seconds, or liter squared divided by moles squared seconds. So we're going to use those units right here. Or you could do liters squared over moles squared times seconds, whatever you prefer. All right, so now we've got all 3. Now let's put this all together into an actual rate law. So let me do some more erasing again. Actually, I have it on the next page. Let's just do that. So here is the summary of the calculations that we just did. And at the end, here is our overall rate order right here. So this is what you would report if you were asked to give the rate law. You need all of these pieces of information. So this is your rate law. And that completes it. You note it has the orders, the exponents. It has the K value. It's actually incorrect because it's missing the units. Let's rewrite this. So it's really going to be the rate is equal to 0.417. And then I'll do the units the other way this time. Liters squared divided by moles squared times seconds times NO squared times O2 to the first. So that's the real rate law because it includes K with units and it includes the orders for each reactant.